Next, we are going to look at vectors. This is Chapter 6, Section 3 in your textbook, found on pages 416 to 421. Let's first start by looking at what is a vector. So a vector is a directed line segment that has both magnitude or length and direction. When you look at this example here, you can see some of the parts of a vector. So a vector always has an initial point, which is represented here by P at the point 1, 2 in this example, and a terminal point, which is represented by point Q here at 7, 9 in this example. The terminal point is always marked by an arrowhead, and that's how you're going to know geometrically and pictorially, really, in a diagram, what part is the terminal point as opposed to what part is the initial point. So let's look at a few other parts of vectors. So vectors consist of a component form. So that vector that I just showed you, I had told you like what the initial point was, what the terminal point is, and when you're actually writing out the vector, you can write it in something called the component form. When you're finding the component form, you are going to take the initial point values and you're going to subtract them from the terminal point value. So you'll take the terminal point x minus the initial point x, the terminal point y minus the initial point y. And notice the brackets that they use here. We aren't using parentheses to symbolize a coordinate point anymore. We're using these brackets to show that it is a vector. And that's going to be really important to identify because there's a big difference between a vector and just a regular coordinate point. The other thing that we'll be looking at is the magnitude or the length of a vector. And the magnitude is found by essentially taking the distance formula, if you remember that from geometry, which is this formula right here. So again, you're taking the terminal point x value minus the initial point's x value, squaring it, plus the terminal point's y value minus the initial point's y value, squaring that, adding it together, taking the square root. If you already have the component form, it's really easy then to find the magnitude. Just a few other items. If the magnitude or the length is equal to 1, then the vector is known as a unit vector, which we'll look at a little bit more later. If the magnitude is equal to 0 or it has a length of 0, it is a 0 vector, and you're not going to see that very often. So let's look at our first example. We're going to find the component form and the magnitude of vector v, that's what we're going to call it, given this initial point and this terminal point. So let's look at component form first. So vector v, notice I'm using my vector brackets. I'm going to take the terminal point x value minus the initial point's x value, comma, terminal point's y value minus the initial point's y value. And I get 8 minus a negative 3 is 11, and 1 minus 2 is a negative 1. So my component form for this vector would be 11, negative 1. Notice my vector brackets. Be very intentional about that. In fact, on WebAssign, when you're doing questions like this, there is an actual vector tab in the equation editor that should show up for you. Make sure you click that vector tab. Make sure you get these brackets when you're typing it in. Otherwise, it will mark your answer incorrect. So just be intentional about that. Let's also look at magnitude. So the magnitude, this is the notation for magnitude. So we're looking at the magnitude of vector v. We're going to take the square root. Since I already have the component form, it's really easy to find this magnitude. 11 squared plus negative 1 squared. So I get 121 plus 1 square root of 122 would be my final answer there. Do not make this a decimal. If your radical does simplify it. Square root of 122 does not, so I'm just going to leave it just like that. Let's look at some vector operations. So there are two main operations, scalar multiplication and addition. So looking at scalar multiplication first, and this is right from your book, In vector operations, numbers are referred to as scalars. Geometrically, the product of vector v and a scalar k is a vector that is k times as long. When k is positive, the vector is the same direction, and when k is negative, the vector is opposite directions. And so you can look at the picture that I have for you here geometrically. So if we start with vector v, if we multiply it by a 2, notice that my vector is still going in the same direction because 2 is positive, but the vector itself is twice as long as that original vector. If we have a negative v vector or a scalar of -1, notice that it has the same magnitude or length, but it is now going the opposite direction. So the initial point and the terminal points actually switch. And then if we have a -2 as our scalar, notice that the scalar is still twice as long, or I'm sorry, the vector is twice as long, but again, it is going a negative direction to the original vector. You can also look at these algebraic or the algebraic definition. So if you have a vector u in its component form in a scalar k, that k essentially gets distributed to both parts of the component form to create your new vector. Let's also look then at vector addition. So if we're adding two vectors, u and v, in order to add them geometrically, you're going to position the vectors so that the initial points are together. You're going to create a parallelogram with the two vectors. So if you look at my picture here, here's my vector u and vector v. I positioned them with initial points together, and then the dashed lines created my parallelogram. The resultant vector, which is them added together, u plus v, is the diagonal formed in the parallelogram with initial points at the other initial points and then terminal point at the opposite side. So this dark blue vector that you're seeing here is actually the geometric depiction of these two vectors added together. Algebraically, you have vector u, vector v. In component form, you add the first ones together, add the second ones together to get your new vectors. So let's look at a couple examples here. So we have vector u and vector v, and we're going to do some vector operations. So u plus v, I have 1, 2, plus 3, 1, and I'm going to show you all the steps on this one. So this is going to be 1 plus 3, comma, 2 plus 1 to get me a resultant vector of 4, 3. 4, 3. So that would be my resultant vector. So what does this look like geometrically? So let me show you a picture. So you can see your picture there. So I have vector u, which has a component of 1, 2, so it's over 1 up 2, kind of like a slope there, and vector v that has the component of 3, 1. Notice I set up my parallelogram, their initial points were placed together, and this blue vector here is my resultant vector, and that's the vector 4, 3. Okay, so that's how that vector addition works. So let's look at u minus v. So I take 1, 2, this time I'm subtracting. I'll show you all the work again. So this time it's going to be 1 minus 3, and then 2 minus 1, and that's going to get me a vector of -2, 1. And so that's the vector represented algebraically. Let me erase some things here, and then I'll show you the vector geometrically. And then there's your geometric vector. So let's take a look at this one real quick. So notice u stayed the same. This time now vector v is negative. So its initial point is still at 0, 0, but it's going the opposite way. Parallelogram is formed, And then this blue vector is my resultant vector, which is -2, 1. Okay, let me just erase, make myself some room here. And the last one, 2u plus v. So this 2 is acting as a scalar, so it's 2 times 1, 2 minus v. So I'm going to go ahead and multiply that first before I do the subtraction. So you're still following order of operations. We need to multiply before we subtract. So scalar multiplication, 2 times 1 gives me 2. 2 times 2 gives me 4. And then I'm still subtracting the 3, 1. And skipping a couple steps here, 2 minus 3 gives me a -1. 4 minus 1 gives me a 3. So -1, 3 would be your final vector there. What does that look like? Here's your picture for this one. So 2u, that u vector was doubled in length. -v, same thing, it's opposite. And then you see your parallelogram form there for your final resultant vector of -1, 3 that you can see in that picture. Okay? Let's do another one. This one I'm not going to show you the pictures, but just going through some more examples. So I have u plus v again. This time my u is 2, 5, and v is 6, -1. And I'm not going to go through all the steps this time, just for the sake of time. So you're adding the first component parts together, so 2 plus 6, which gives me 8, and then 5 plus -1, which gives me 4 for a final resultant vector of 8, 4. And notice here too that I'm still using the vector brackets. So you got to be very careful about that. Your final answer is still a vector, so you're still using vector brackets. So next one, u minus v, so 2, 5 minus 6, -1. Just subtracting 2 minus 6 gives me a -4. 5 minus a -1, that double negative makes me add, and -4, 6. Okay, and last one, so 3 times 2, 5 minus 4 times 6, -1. We are going to multiply both of these first, and then we'll subtract them. So 3 times 2 gives me 6, and 3 times 5 gives me 15. I'm keeping the negative. You can also think of this as multiplying by a -4 and changing it to addition. Completely up to you. I'm just going to keep the negative and keep it as subtraction. So then I'm doing +4 times 6, which is 24, and +4 times -1, which is -4. And then I'm going to subtract my final answer. So 6 minus 24 is going to give me -18, and 15 minus a -4 is going to give me 19 for a final resultant vector of -18, 19. We'll stop here for this video, pick up on part 2 of vectors.